Hello there. This is Universum, the place where we learn about the entire universe, how it began, and how it will end. Today we're going to be talking about differential equations and how to solve them. Now lately I have been going over a bit of the Maxwellian equations, so today I'm going to be talking about differential equations, how to solve them in two ways, which would be called shields, which would be an acronym. Shields would be an acronym for separable, homogeneous, integrating factor, exact, linear, direct integration, and substitution. And then there are also odes. Now, odes basically just ordinary differential equations. That's what it means. Now, odes isn't necessarily a way of solving it, but it basically just gives you a little of a factor of a way to solve it. So, like, for instance, basically what ordinary differential equations means is it's sort of differential equation that it's not like the partial differential equations as most of the Maxwellian equations are. But yet, they're a little bit more complex, although it's a little bit interesting since partial differential equations are longer than ordinary differential equations, but ordinary differential equations are shorter than partial differential equations, which is very, very interesting. Now, in order to find out what any of this stuff means, we are going to need to get into shields. So first, let's say we have a differential equation. Let's say y prime, which then would be equal to the function of x dot y. Well, let's try to solve this differential equation using shields. Is it separable? Yes. We could solve it now, the way that we could solve it is that we could separate it into its derivative forms by putting, let's say, the derivative of y prime over the derivative of x. Well, squared derivative being a constant, that could be set and fluent throughout the equation. Then there's h, which then will be homogeneous. So what we could do for that is then we could instead of doing just the derivatives, what we could do is that then we also could separate the function of the equation, and then we could put the y and x notations instead of now on the other side of the equation, due to it being a function, instead of making it the derivative of it, since we already know the derivative of it, we'd have to set a value to the function of them. Instead, what would happen is that then we put brackets over these, due to these being an independent variable, and then what would happen next is then we do y over x. Then what we do is that then we do integrating factor, which usually is the longest way to go. But let's just go a little bit over to exact differential equations a little bit next, which is the second longest, actually. Now, usually exact differential equations are a bit shorter than integrating factor differential equations, although I do want to go over integrating factor a little bit, just so you can get a bit of an idea of what they look like. So first, we're going to need to make an interval of an equation. So we're going to need to do an interval range of a certain range between the set value of y and x. So first, we're going to need to solve for the derivative of y and x first. So all we know is that y is over x. It means that y is greater than x, or it could mean y is divided by x, or it could mean a multitude of things. But what we need to do is that we are going to need to separate them from time-independent derivative of the function. And then when we set the range of the integrating factor, what we're going to need to do next is that then we're going to need to try to find the exact factor, which then will be solving for the functions of the equations and then putting it throughout the equation. Well, it's almost like combining terms a bit, but not exactly. Then L would stand for linear. Linear meaning that, yet again, more derivatives, which then that will be added to a certain function of the two time-independent variables. Then D would stand for direct integration. Now this one is one of the most simple. This one is one of the most simple of them all. Simply, all you do is simply just separate the two functions into their time-independent derivative functions. You make them over one another. So let's say you do the derivative of y divided by the derivative of x, which then would be equal to the function of x. That would be what it would look like. And then S would stand for substitution, which can mean a multitude of things. It can mean many, many, many things. So now that we have a good idea, we have a good taste of what differential equations are a bit like. Now we want to understand why are they useful? Why do we even want to even bother with differential equations? Well, there's many, many reasons why. And that has to do with the way planetary motion works, as explained by the Keplerian orbits, as explained by Gauss's theorem, Gauss's conjecture, which basically now in order to get a grasp of all these topics, we first have to let's look at the easiest one, which would be Gauss's conjecture. Gauss's conjecture, what that would be is that would be the log of 1. Yeah, that's basically all it is. Basically just be a logarithm, then that'd be over 1. It's really, really simple stuff. This also has to do with a way of solving the Riemann hypothesis. This is one way how Riemann actually came up with this hypothesis. And many physicists are still trying to solve it to this day. Yeah, so you're probably wondering, well, what is the Riemann hypothesis? Or if you do know, then what does the logarithm of 1 have to do with the Riemann hypothesis? And if you know both of them, what they mean, then you probably are wondering, why does it work? And if you do know why it works, then please click out of this video now. Or if you do know how it works, and if you don't want to click out of this video now, then you can definitely continue. So first, the way it works is that we need to understand a bit of Taylor series first. So Taylor series basically means that you can take a derivative interval of a certain function, and then as you keep on growing the interval, you get more approximated, more and more and more, until you basically get on to infinity. You can get, but you'll never get that. You can never get directly to infinity, but you can get close enough to infinity. But then again, infinity is infinity. In fact, even a Googleplex, any number you can think of, will be as far away from infinity as 0. So ultimately, you can get as close as you can possibly get, but you'll always be missing that last decimal points. And this is what Gauss's conjecture is. Basically, what it thinks is that it thinks of primes. As you go up in the primes, well, you get more and more approximated as you go up in the numbers. As you go up, isn't like, for instance, Gauss, when he was about 12 years old, he calculated over 1 million prime numbers. And it's very, very interesting. Since prime numbers, they probably are one of the, at least when you're talking about Pythagorean triplets, that's what's getting a little interesting about them. Of course, everyone knows that prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, and so on and so forth. But what people didn't realize is that, let's say if you were to make instead of a 2-dimensional plane, you made a 1-dimensional plane, but except its y-axis was imaginary. It was represented by the number I. So what's happening here is that when you represent it by the number I, you possibly could get a Pythagorean triplet. So what happens is that as you go up in numbers, what Gauss did when he was young is that every single time a number was a prime, it went up. Almost like a descending staircase. Then as soon as he got to the millionth prime number, I know that's a lot of prime numbers, what happened was that he drew a line through them. Well, at least a semi-line. And then what he noticed is that it looked exactly like the logarithm of 1. And he thought that this had to do something with something. And this is one thing that Riemann thought of. Since Riemann was one of Gauss's first students, he also was one of the most gifted. Now, the interesting thing about Riemann is that when he was making his theory of what would happen if you were to make a sort of prime number spiral, so the way it is that instead of just making an imaginary plane along with a straight line going through it, the imaginary plane and the real plane, what would happen if you were to actually curve the plane, warp it, and then put the prime numbers? You no longer had a logarithm. Instead, you had a spiral. Just spiraled around. the crazy thing is that, so let's say if you were to plug this into a Fourier transform, it would look exactly like what would happen if you were to plug in a sine of 1 this time. So there's no longer a logarithm of 1, it's a sine of 1. And this is when things start getting really confusing. And that is when his theory was created, Riemann's theory. Well, it's more like Riemann's hypothesis, but many people consider it a theory, many people consider it a hypothesis. And it's one of the craziest things to this day. And that is one thing differential equations could possibly be able to solve. We could possibly, in the far, far future, be able to solve this equation. But to this day, as far as we can tell, no one has solved it. And there's one case that was really, really close of someone solving it, although he said that he didn't want to tell anyone it, and then, well, years passed, people were begging him. It's almost like Cryptos, the most famous code that most code breakers around the world are trying to crack. But nobody can crack it except for one person, the person who made it. Well, he died, and well, his documents were burned. Nobody knows where they are. And to this day, nobody knows how to solve the Riemann hypothesis. In fact, it's in a really simple algorithm, though. It's really, really simple. All I need to do is you just need to just plug in a function. You just need to just plug in a function of zeta. That's like what Riemann made. It's called the zeta function. And then what happens is that so as you keep on going up in the function, so what it looks like is that it looks like zeta meaning the Greek letter, and then it would be the time-independent function of s. Now s is the function we're trying to solve for, and then s would be equal to the sum, which then would be equal to the infinite sum of a Neumann function of 1, which then the sum would be equal to 1 over the Neumann function of s. And s is what we're trying to solve, but yet we can't. So that's quite interesting. And the fact is that this theory is that you will literally get $1 million if you solve this theory, but yet nobody around the world has solved it. And hopefully sometime in the far future, differential equations will help us. I know they will. Another way that differential equations are useful is that they also could be useful for possibly cracking the time-independent Schrodinger equations. Schrodinger equations, they are brilliant. Like, they are just brilliant equations. Now, basically, it's like what it says is that, so it means the negative h bar of 2, well, negative h bar squared, like you can say in any way you want. H bar meaning Planck's constant, and then that'd be divided by 2m, m meaning the mass of a particle, or it could mean basically anything of a particle that could be trapped in a Heisenberg uncertainty, which then that'd be multiplied by the differential squared of the wave function, represented by the Greek symbol of psi. Psi meaning the wave function of a certain oscillating type of wave duality particle, which then that would be divided by a differential of x squared, which then that would be equal to I meaning a certain type of function, which then that would be multiplied by h bar meaning Planck's constant yet again, which then that would be multiplied by a differential, not squared this time due to it being a constant throughout the equation, of the wave function, which then that would be divided by a time-independent value of the differential of time. Now, what all this means is that a particle could be in two positions all at once. So let's say if you were to take a particle's mass, and then if you were to take it into a actual multi-particle being, let's say a cat, for example. Of course, everyone knows this. Schrodinger's cat, obviously. But yet this time, this creates a weird sort of function, and this could end up in the many worlds hypothesis. So what if instead of putting the cat in the box, we put the physicist watching the cat in the box. And then we put not one piece of radiation, but a perplexion of radiation sources for the Gaussian counter to detect. Obviously, this obviously does not be a random Schrödinger, but except these physicists would almost certainly die. But yet, if the main world hypothesis is true, this could result in a quantum immortality. That's what it's called. So what if you were to example? So of course, in your world, the physicists may die. Of course, what that would do is that then that split up the wave function duality based off your conscious observer. But then again, but in some other one of the many worlds, could there be a physicist who survives this cataclysm of beta, alpha, and gamma particles smashing the gamma ray, smashing the Geiger counter detector, making it beep off like crazy? There's a small chance, and this could result in quantum immortality. This means that in this world, this many worlds, there could be a perplexion where possibly the physicist could survive and result in a sort of quantum immortality where the wave function has collapsed. This results from, as said in the Copenhagen interpretation, that this could possibly prove the Copenhagen interpretation correct, meaning that just you being conscious, watching this video right now, you could break the wave function. You could smash it just by looking at a particle in a superpositionized state. Well, but then again, this is really easy to understand. Since basically what happens is that it's almost what happens if you were to make the double slit experiment, as said in pilot wave theory by Louis de Broglie and David Bohm. So basically, what happens is that, let's say if you were to put a particle detector at each one of the slits, well, what happens is that the particle, it wouldn't want to behave like a particle anymore. Instead, it behaved like a wave. And then if you take it away, it want to behave like a wave again. And then it becomes really interesting. This is why Schrödinger's equation is so useful. It predicts quantum behavior. But how is that possible? If particles can be in a superpositionized state, but yet particles could be in a multitude of, but yet particles could also have an uncertainty of states, as said by Heisenberg's uncertainty principle. Which, by the way, in case you're wondering, which basically the Heisenberg uncertainty principle would be delta in P, which then would be multiplied by delta in X, which then would be equal to H bar divided by 4 pi. In case you were wondering, of course. Yeah, but the crazy thing about this is that how does this work in these equations? Well, this is one reason why Here's one reason why even the most smartest, the most gifted mathematicians in the world even say this: differential equations are really hard to solve. That's what they are. That's just their nature. But then, in case any of you are wondering, any of you who know differential equations like the back of their hand were wondering, you might have said, wait a minute, you forgot one thing at the time I finished Schrödinger equation. You forgot the Nabla operator. And yes, you are correct. I did forget the Nabla operator. Thank you so much for reminding me that. So Nabla, in case of you who don't know what Nabla is represented by two names, and it can be represented by del or Nabla. Basically, what it looks like a upside down delta symbol, or those of you who don't even know what delta is, it looks like an upside down triangle. So what Nabla is, or del, if you want to call it that, is used in mathematics as a particular vector. Let's say if you were to have a curl or divergence field, it's sort of vector field, a field that is full of vectors that are just rotating. This is rotating and oscillating around a sort of planar axis. And this creates the operator. So what happens is that when the function is defined by one-dimensional domain, it demystifies. Well, not necessarily demystifying, but it overthrows its standard derivative as defined in a certain type of function, as explained in vector calculus. Now, this nabla operator is extremely useful for many, many things. And one of them, including, is that the nabla operator is extremely useful for the time of extraordinary equations, and even Bell's theorem of polarization, where the photons be polarized as a type of linear axis. Like, for instance, the light is bouncing around my room right now. What's happening is that the photons, they're in a sort of wave, they're in a sort of superpositionized function, not only in their wave function, but also in their polarized state itself. Now, what's happening here is that when these particles are passing through the blinds over there, not only are they in one polarized state, but yet they're in a multitude of them. See, now, from my consciousness observer, I don't really see that many of them passing through the window, but yet on this camera, you are seeing a multitude of them passing through. Well, for one, there are two reasons why that's happening. For one, the camera's polarization filter, well, of course, it allows more and more photons through due to a sort of probability amplitude that's happening. And of course, many of you know this, and then this would be called the harmonic oscillator, of course. And another reason why is because, well, humans' eyes, they don't necessarily get polarized exactly to the right amount of length, but yet also another reason why is because, well, humans' eyes have thousands upon thousands more resolution points than a computer's camera will. In fact, against many other cameras will. A human's eye is more superior. That's why if you're looking through a telescope, let's say for instance, you will actually see more through your eye than you will just by taking one shot through a camera. Although cameras, they need exposures, they need subs, they need many, many things that could help them gain more photons that are superpositionized states. But yet, a human's eye can get all these subs all at once. And that questions the way our consciousness behavior works. Why does it collapse the wave function? Why does it destroy the time and extraordinary equations? And what happens if you were to have two conscious observers all at once? And then if you were to have many superpositionized particles, would they see the same thing? Would one of them, would they both be entangled with one another? All these are correct in a superpositionized state. Since what happens to the observer is that, well, whenever, let's say if you were to have the cat in the box experiment again, let's say for instance, or even the double slit experiment again. Well, what would happen is that the observer would become entangled with the photons or the cats or whatever that are superpositionized states. It would become entangled with it, and so would the entire universe itself. It would all become entangled with it in a sort of mystified state. And then whatever state it becomes, every single other thing in the universe will become that state as well. And this is what the so-called Boltzmann's brain is everything based off of probability. And what is probability exactly? Of course, this is a really simple question. Basically, this means a certain type of amplitude of a certain type of wave function, or a certain type of comparison. For example, let's say this deflated balloon, for example. Now, on a ratio between air to silicon on the inside of it. Now, what is the probability that there will be more air than plastic? Oh, so silicon and carbon. Very, very low. That of course is a probability amplitude right there. And this sort of wraps up the beauty behind differential equations and the beauty behind the majesty of it. Majesty of the beautiful quantum world, the way that can behave, the way that everything could be brought up and could be controlled by a single particle known as a pilot wave. Thank you so much, everyone, for watching, and I'll see you next time.